Hello everyone, and welcome back to episode 12 of JNSQ. We left off last episode just having set up our first deployed science base on Minmus. Today I mentioned that we're going to be doing something a little bit more interesting, I guess you could say on the theory side, but something that should be very useful for us going forward. Today, we'll be playing around with satellites and reference frames, as the title of the video may suggest to you. I'm tired of losing signal on probes that I put in orbit when I'm trying to do some maneuvers on them, so today we're going to solve that by setting up a set of relay satellites. This rocket is actually the second of 3 satellites to launch. Setting up geostationary satellites with the Principia mod actually can make things a little bit easier, which we'll see in a few minutes. Now, the geostationary altitude for Kerbin in the JNSQ mod is a little bit under 9 megameters. So the first thing we're going to need to do once we have the satellite in orbit is conduct a maneuver to raise the highest point of its orbit to this altitude. Now, once this first maneuver is completed, we're actually going to work on our flight planning using a different reference frame that we've seen before, the Kerbin-centered Kerbin fixed. Recap that this is a quote-unquote rotating reference frame that rotates with the planet's surface. So essentially, in more simple terms, it shows the path of the spacecraft relative to the surface of the planet as opposed to relative to space as a whole. Now, we can use this to our advantage. Normally, in the stock game, or when we're using an inertial reference frame, if we go in the map view and plan our flight so that the highest point in our orbit appears to be above a certain point on the planet's surface, it isn't actually going to be representative of where relative to the surface the spacecraft will be, because the reference frame that we're operating in does not take into account the rotation of the planet's surface. Here, however, since that's the entire point of this reference frame, we can intentionally plan our flights to be above a certain point on the planet's surface at a certain time. Now, we're going to want to have 3 satellites in total here. That should give us pretty good coverage of the planet's surface and the space around it, with the minimum amount of effort and money required. The way I'm planning to set this up is just to have one satellite pretty much directly over the space center, then one 120 degrees ahead, and another one 120 degrees behind. Now, as we approach our circularization burn for the aft satellite, which is the one we saw launching first, you may notice something peculiar in the flight planning. When we do our burn, the flight plan looks like it's set to just kind of stop at one particular point. This is actually the hidden trick I was talking about, with Principia making it kind of easy to do geostationary satellites. Keep in mind, we're trying to put a satellite in an orbit that is specially designed to keep it in the same spot above the surface as best as we can. And therefore, logically, when we put our satellite in that orbit, the flight path in this view of the orbit that respects the planet's surface should wobble about one particular point. After the maneuver, we have to do some manual adjustment with a pretty low thrust limiter on the engine. And as you can see, the markers for the orbit slowly converge into this one point. After this correction, we can put the simulation many steps ahead and see that indeed the path of the satellite shows it not moving around that much, which is exactly what we want. The front relay is up next, and we're going to be doing the same thing. Similar maneuver with the markers converging ahead and probably some corrections afterward. You may also see on the nav ball one more thing that's telling us that our orbit is indeed in the right place, which is that our velocity in this reference frame, our velocity with respect to the planet's surface, is very, very low. Now, you may be wondering how we even figure out what the altitude is that we need to orbit at to get an orbit that is geosynchronous or keosynchronous, as I've heard some people refer to it in Kerbal Space Program. The devs were helpful enough to include the synchronous orbit altitude for the planets in JNSQ in the celestial body info doc. But in the absence of being told, there's actually an equation that is derived from Kepler's laws of planetary motion. Now, when you put the laws of planetary motion together, you can construct these two equations. They're essentially the same equation, but just rearranged using algebra depending on what information you have and what you want to find. In our case, we have to use the bottom equation, which says that the semi-major axis of our orbit is equal to the cube root of the gravitational constant times the mass of the planet times the period of our orbit, which in this case we want to set up to be 11.967 hours, divided by 4 pi squared. In our case, the semi-major axis is essentially the altitude of our orbit plus the radius of the planet we're orbiting around. Since the gravitational constant is just a fixed number, and we also know how long we want our orbit to take, and we can also find the mass of the planet either in-game or also in the info doc, we can plug all these values in and calculate an answer for us, which agrees with what's in the info doc within a margin of error. After our last satellite is set up, we can look at the ComNet view and see the nice triangle of signal between our satellites around Kerbin. There's one final ComSat I'd like to launch for now. Now, in Principia, all of the celestial bodies in the system can pull on a spacecraft, which opens doors to more complex and realistic orbital mechanics. I'm going to try something new for me, a little bit experimental, and I'm going to try to put a ComSat, the same as the ones we just put up, into one of the Lagrange points around the moon. Lagrange points, in essence, are places in space where the gravitational pull of two bodies has an equal amount of force. The most recent update to Principia added a convenient new reference frame type, the Lagrange frame, which shows the contour lines of gravitational potential energy between two celestial bodies. It's essentially like a contour map, like one you would find of the surface of the Earth, which shows you what areas are higher and what areas are lower. Now, this isn't an exact analogy, but you can use these equipotential lines and imagine that the spacecraft is sort of like a ball you're placing on the hill. If you put the ball down too close to one of the bodies, then it's simply going to get drawn in to whichever one it's closer to. However, there are 5 particular points where there's a more stable region for the ball to be placed down on. 2 of these are a little bit more obvious and are off to the side of the Moon along its orbit. These are known as the L4 and L5 points, and these 2 Lagrange points are considered to be stable. You can place a spacecraft or any other object, hypothetically, around these 2 points, and it will stay there pretty well. There are 3 more Lagrange points that are basically on a line between Kerbin and the Mun. There's one in between the 2 bodies, there's one on the opposite side of the smaller body, and there's a 3rd one on the opposite side of the larger body. In the equipotential plot, these Lagrange points have an X that crosses through them, which is a representation of something fairly important, which is that these points are not stable. You can have orbits around them that are reasonably stable and that you only have to correct every once in a while, but any object that's placed there will eventually drift away. This is because, unlike the L4 and L5 points, where you're essentially at the flat top of a hill, where if you set the ball down, it's flat enough that it won't really want to roll away, these Lagrange points, using the hill analogy, would be kind of in the shape of a Pringle. The ball wants to roll down the Pringle towards the middle with regards to left and right, but once it gets there, it can very easily roll down from front to back. Mathematically, these are known as saddle points. We're doing a maneuver here that's similar to a Mun transfer, but it's off to the side, and we're aiming at this region of stability ahead of the Mun in its orbit. Once we're in high space near the Mun, we're going to do a maneuver to slow down in the Kerbin-Mun Lagrange reference frame. And you can see here that we have this very weird looking trajectory that kind of meanders around back and forth around this area. The path seems extremely chaotic and unstable. However, if we put the projection up more long term, we can see that the satellite will still remain meandering about in this region. With this satellite set up here, I'm not quite sure how useful this satellite is as a comsat. It's so far from the Mun that you might as well just connect directly from the Mun to Kerbin. But it is interesting and new territory for me, and I'm glad they added this new reference frame feature to make these sorts of missions easier. With that mission done, there is one more thing I have on the agenda for today. We recently unlocked the surface deployed weather observation, which only runs in bodies with atmospheres, and so it's a good time to set up a station for deployed science around Kerbin. Now, I want a place to set up that isn't too hard to get to, but I also don't want the experiments to keep getting loaded and unloaded all the time, because that's just asking for a Kraken attack. So I set up our leapfrog plane here with experiments in the cargo inventories of the passenger cabins. I'm bringing a pilot, a scientist, and an engineer aboard, and we take off from KSC here, looking at the map for a good place to land. I noticed that there's an island that's not too far away in sort of the northwest direction. I headed up here flying south of the island, and that way, when we're going into land, we can be traveling closer to south-north, which is a longer distance along this island than just going straight east to west. When we're ready, we do a banking turn to line ourselves up. We prepare for the landing like any other, but with the gentle slope terrain and no hard restriction on directions. I had to keep an eye here on the radar altitude, while keeping in mind that my vertical speed is not exactly representative since the terrain is going up and down underneath the plane. We made a pretty clean landing, and we drove a bit further down the island to set up so that we have some space to turn around and take off. On the ground, the crew shuffle seats. Edgis is out first to deploy the 2 science experiments. I actually lowered the plane down to the ground, which looks funny, but it's easier for the Kerbals to get back inside. Joffred greets him outside and sets up the solar panels and control station. She also plants a flag and conducts an EVA report and collects a surface sample while outside of the craft. With everything set up, the crew can all pile back into the plane. The takeoff went pretty smoothly as well, although it was a little bit tough because the plane wanted to lift off the ground at too low of a speed for it to actually get enough air under its wings. After a short flight back to the Kerbal Space Center, we have an ironically bumpy landing on this straight paved runway. However, we recover the plane safely, and we can let the surface deployed science run in the background while we work on other things. With that mission complete, I'm satisfied with some of the new territory that I've explored in this video. I think that the ComSat network around Kerbin is going to be very helpful with transmitting data and making sure that probes aren't annoyingly out of signal at inconvenient times. However, you're going to have to tune in next time to see what use we can make of these satellites. Thanks for watching, and take care.